My brain sort of refuses to learn this technology. I don't know about you guys, but I'm Zoom resistant. If hopefully not, that's all I'm resistant to. So the topic I selected for my talk today really tries to capitalize on my training and what I see as some common things in the audience, which is that I have training as a linguist and a cognitive scientist, and I have landed in a speech, language, and hearing department and in a psychology department. And so, much like the audience here, I feel like the study of language in general, but especially the study of language in the brain, really can draw on a lot of strengths from those different disciplines. And I hope there's a little bit of something for everyone, I hope, in this talk. But because of that, it's a bit wide ranging. And so we'll hope we get to the end, but there's a cut point where we can stop things if it's a good time to move to questions. So the question that I wanted to consider today is one that I think is near and dear to many of our hearts, which is, what is the difference between native language perception or comprehension and non-native language comprehension? So just by way of anecdote, when I moved to Rhode Island to start my graduate work at Brown, I was coming from Iowa. I don't know if anybody know dialect differences, but Iowa and Rhode Island have pretty different dialects, which I was utterly unprepared for. Matt knows what the Rhode Island dialect is like, right, Matt? It's completely different than what I was expecting. I had to learn all of the phonetic differences that characterize that dialect, as well as other kinds of differences, and adapt to that dialect relatively quickly. That process to us feels fairly easy. We go through the world doing that kind of thing all the time, adapting to language variation, whether it's on the individual basis or the dialect basis or non-native accent basis. By contrast, we have this feeling that, at least in adulthood, learning non-native sounds is very, very hard. And the traces of that, of course, are seen in the difficulties that even very proficient non-native learners have in their phonological structure. They may have, for instance, accented speech when they speak. I know I do in my heavily accented Spanish. And we also have the same kind of accents as we listen, right? The perception of those non-native categories can be very difficult when we've learned something in adulthood. So what I want to do is consider this problem of understanding speech categories. Now, moving back to this question, many of you say, but of course, there's so many other things that are different about the native and non-native phonetic perception system. 100% agree. There's differences in proficiency with vocabulary and grammatical structure and other rich things that many of you know more about than I do. But considering the phonetic category specifically, I think we can think of this problem of non-native learning and native language adaptation or shifts in perception as potentially relying on some similar types of processes. So to make this a little more concrete, here's a cartoon. So let's imagine that this is your acoustic space, and each of these little blobs are different acoustic tokens in that space. And the red ones are one type of category and the blue ones are another type of category. Well, if I am undergoing the process of listening to someone speak, I may have to learn, for instance, that in a particular context, the boundary between these categories could be shifted slightly. So, for instance, in fast speech, the boundary between sounds could be shifted a little bit to accommodate for fast versus slow speaking rates. I also, if I'm learning a non-native category, have to cope with this, or a native language category, have to cope with this fact that my perception isn't actually probably veridical to what I'm getting in the input, right? That we seem to have kind of perceptual warping around category centers in our native language, such that not all tokens are really perceived as equally distant from each other, even when they're equally distant in phonetic space. And then we have this interesting problem when we go to learn a non-native contrast that falls within one of these contrasts. So I'll use an example that comes up a lot in my own work and in a lot of the work on this topic, which is the Hindi dental and retroflex contrast. So this is unfamiliar to you. In my English, I have a category duh, like as in dog. In Hindi, there are sounds the and duh, one with the tongue behind the teeth, one with the tongue curled up. To my ears, those are very, very similar sounds, really hard to distinguish. And in fact, both fall as good examples of that D category for me. But if I'm a Native American English speaker learning Hindi, I now have to crack apart my D category in order to hear the differences between those sounds. That's going to be a real challenge for me. Another thing that is a challenge that we have in both native language and non-native speech perception is learning to generalize, right? So as I've been speaking, you've been learning something about my own dialect. You probably have gleaned information about my likely dialect background in the US, something about women of my age and my size that has probably helped you in categorizing my phonemes. And that may or may not be useful information when you encounter my daughter for the first time, who has similar language, but actually rather different phonetic categories. So that kind of generalization problem is another challenge for both the native and the non-native speech perceiver. And then whatever we've learned, we have to maintain it, right? So whether we've learned about a new talker or we've learned about a new language, we need to be able to maintain that information over time. This is something that I think people who are interested in language pedagogy know really well, right? They know their students don't necessarily retain information as well as they might hope. But those of us doing lab-based studies often neglect this issue of maintenance and how do we maintain this acoustic information and its mapping that we've learned into the next week, the next year. Okay, hopefully I've given you sort of a bird's eye view of this process and how it could be similar between these types of learning. And so really we're going to spend the rest of our time with this question. Do we use some of the same machinery for native and non-native speech perception? And this takes me on a little bit of a funny path through my own work. Some of it's rather old, some of it's rather new, but hopefully we'll find some places where it sticks together. So what we're going to try to do is look for similarities and differences in a sort of 3 domains and a fourth if we have time. One question is, are we using similar neural mechanisms for perception of native and non-native contrast, and in particular adaptation to or learning sort of the new categorical information about those categories? A second issue I'll turn to is the role of sleep in this process. So does sleep have similar effects when we're considering native and non-native speech sound learning? And then we're going to dive into an individual differences question. So really the question here is, are people who are good at one kind of learning also good at the other kind of learning? This is a question that I think people who are in the business of worrying about speech and language disorders, as I am, will find some resonance with, because we know that there's a lot of individual variation in the population that we really haven't explained yet. Okay, so let's get into this. Our first question is really going to deal with these context-sensitive changes in perception. And here what I mean are changes in adapting to the speech of a particular talker. So we know that every talker employs his or her own idiolect, right? There are idiosyncratic things about the way that I talk that aren't even necessarily predictable on the basis of my dialect or my size or my vocal tract length, but just weird things about me. It seems like we are pretty good at attuning to these acoustic features of people's speech and maintaining them over time. The way that we get to this experimentally is through a lot of routes, but this is a paradigm that I'm going to introduce to you that has been used a whole lot, not invented by us. It goes by a lot of names, annoyingly enough. You may have heard this referred to as perceptual learning for speech or lexically guided perceptual learning. Both are kind of a mouthful. But here's the way it works. What we do is we take a blend between the S and the sh sound, in this case, 2 phonemes. Here we have, you know what, I think I shared this without the sound. So I'm going to stop my share for just a second and share with sound so you'll be able to hear this. Pardon me. Okay, hopefully this will do the trick. We're going to take these 2 sounds, we're going to blend them together so that we have the first word,
rehearsal.
The second word,
rehearsal.
Okay, now we're going to take that middle portion, take them out and blend them together. This took me a long time, but I did it a while ago. And we're going to stick it back into that word.
rehearsal.
Okay. So for me, what I hear is rehearsal, the word like orchestra rehearsal, with maybe just a slightly funny quality to that medial fricative, maybe a little bit of a sh sound in that medial fricative. Typically, our participants don't even notice when we've done this, right? And the reason is that they've used that lexical information to fill in the gaps there and easily resolve the ambiguity in that medial token towards the sa, because rehearsal is a real word and rehearsal is not a real word. Kind of doesn't matter how you do this. You can actually expose people to these sounds in a lot of different ways with a lot of different tasks, but we did a lexical decision. So they had to decide whether these words are real words or not. They've done that task, we set it aside, and then we bring them in and we have them simply categorize sa and sh sounds from a continuum without context. So the sounds sound like this, but they'll be randomized.
Ashi, 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 ashi.
You get something more sa-like to something more sha-like. And the typical finding that's been replicated many times, and again, this was not invented by us, is that we see a shift in your categorization of those sounds that's consistent with what you heard before, right? So if you've heard that ambiguous sound in an S bias context in a word like rehearsal, you're going to interpret that ambiguous sound as belonging to the S category. A different group of people will hear that same sound, but it's going to be embedded in a context like ambition, where it biases you toward the sh sound, and they'll shift their category boundary. So we take this as evidence that you've learned something about this talker, right? You've learned that this talker has slightly strange alveolar palatal fricatives, and you're going to apply that knowledge when you hear that information the second time. So what we did is we plopped this in the scanner, and we had people do essentially the same task. Now, I'm going to kind of dive right in on brains here, but you probably already know that the architecture for perceiving speech sounds primarily relies on regions that are a little more posterior in the brain, the posterior temporal regions bilaterally. What we found was, interestingly enough, that there was more involvement of frontal areas than temporal regions. And this is a pattern that we've seen fairly consistently. I'm not showing you very rich data here. I sort of don't want to spend too much time on this, but essentially regions in left and right frontal areas were the first to show sensitivity to the sound contrast. And only over time did that information become encoded in posterior temporal region, sort of its home, where we would expect it to live for native language processing. So that categorization and adjustment seems to happen up front in sort of more executively linked systems, and then over time seems to be transferred more posteriorly to really guide and tune up the perception of those sounds. That's the model we're working with. So filling in our chart here, we have this frontal to temporal sort of movement that might be going on. What happens when you're listening to non-native sounds? So similar issue, right? Again, we have to take this complex space. We have to find the boundary through it. In this case, rather than shifting a native language category boundary, we're going to take this acoustic space and crack apart two existing phonetic categories. So what that looks like is the following. We take a continuum of sounds. In this case, it's a d, d to g continuum, actually. It goes all the way through those phonetic categories. And just to account for the fact that all of these sounds aren't created equally, what we ended up doing is basically dividing our subjects into two different groups and training them on two different boundaries. So if you were a retroflex velar trainee, you were trained that all of these categories, or all of these sounds rather, belonged in the A category, and this one belonged in the B category, just kind of like English actually, right? So these sounds are liable to sound like D sounds, and this is liable to sound like a G sound. And then the other group was trained to instead group these three sounds as A's and these six sounds as B's. And they were simply done this by presenting a sound, feedback, and you iterate on that until they get reasonably good at it. And they do. It's tough, but they do get better and better at it. Then what we do is we stick people in the scanner. And here, what we're really interested in is the difference between the two groups, right? Because they've learned to group these sounds in different ways. The top group has learned that these sounds are equivalent, but these are different. And the bottom has learned the opposite, right? That these are from different categories and these are equivalent. And given what we know about the structure of phonetic categories, that should be sort of visible in the neuroimaging data as differences in sort of the magnitude of the response as we move between categories. And indeed, that's exactly what happens. So you'll see again that what we're seeing here are the frontal areas are the culprits. These are the regions that, at least in early stages, are the first to develop sensitivity to these sound contrasts, okay? So they're really showing differential activity according to whether you, as the participant, was trained to put those sounds in the same category versus a different category, okay? Now, this was a one-shot deal. This was a one-session kind of training. So we didn't have the advantage of looking at sort of longer elaboration of this training, but really great work from Bharat Chandrasekaran and Fong and Yi, his trainees, has shown that it looks like indeed what we see are these sort of frontal structures are the first to show similarity differences. Here they're looking at native versus non-native speakers of languages, but over time, the people who are the most proficient learners come to have these more posterior similarity spaces that most closely resemble native language perception. So that frontal to temporal transformation, I think, has been shown in other sort of domains as well. So again, from a bird's eye view, we've got a similar kind of deal going on. We have, when encountering these sort of challenges that force you to change a category boundary, that force you to carve up your acoustic space slightly differently, in both situations, we begin with frontal involvement and it gets transferred back to more posterior regions. So suggestive maybe, but probably not the end of the story. Let's look for other kinds of similarities. I'm now going to switch gears a little bit and introduce you to a line of work that kept us busy for a little bit. We're not really doing these kinds of studies anymore, but was sparked by a former graduate student of mine who was interested in memory consolidation and sleep, and came to me with the question, we know that sleep is effective for consolidating words during word learning. What happens with phonetic category learning? And advisors, this is a good reason when your students come to you with these kinds of questions, say yes. These end up being the most fun and interesting questions to go after, where you say, I have no idea, let's go figure it out. So what affects speech sound learning? Well, language researchers out there know there's tons of stuff that we know affects language learning in general. Things to do with brain morphology, things to do with genetic variation, your auditory encoding ability, things that are a little bit more within our control, things like your training environment, the pedagogical situation, the kind of reward that you get. But we're going to focus on this very sort of narrow view of this, how sleep affects this process. And the way that we predict that sleep is going to affect non-native learning is really in two sort of hallmarks. One is that we know that sleep is important for memory maintenance, right? So that's not surprising to you. And one common phenomenon, I think language teachers have this, speech language pathologists do as well, is that they will find that something might get mastered really well within the classroom in one session or within a therapy session. And then your client comes back a week later and it's like you're starting from ground zero all over again. So we wondered if part of the challenge in non-native learning, and perhaps other kinds of learning as well, is really in this maintenance phase as much as it is in the learning phase. And then the other thing that we know sleep is useful for is in going from specifics to abstraction, right? Going from instances to generalizing to other sensible situations where we should generalize. So we thought we might look for effects of sleep on both of these processes. And don't take my word for it. This is a really rich tradition of sleep research, both in and outside of language, involves motor learning literatures. Gareth Gaskell is one of the pioneers of the way this has been applied to word learning. A lot of really rich stuff to explore there to get into what sleep does for perceptual skill learning and abstraction. The way we decided to approach this, and by the way, this is really driven by my former graduate student, Sayako Earl, who's now at the University of Delaware. We thought, well, let's put people in this kind of training situation, right? These sort of artificial training paradigms that we often use. And what we're going to do is we're going to assess their ability, participants' ability to learn Hindi, dental, and retroflex contrast, one of these very difficult ones. In this case, what people actually did is they learned to pair the sound with this funny little novel object. So it was kind of like a word learning study, although I wouldn't push on that very hard. They learned that the one on the top was a dug and the one on the bottom was a dug. Then they got training. So first they just discriminated sounds and they got training on those sounds. Then they identified them without the feedback. And then we reassessed how well they could discriminate between these sounds. And the idea is you should get better both in being able to identify the sounds and also to be able to discriminate between dug and dug in a minimal pair situation. That's been done a lot. Sayako's innovation here was to divide people into 2 testing groups and basically stagger the schedule of training and testing so that sleep fell in a different window for these 2 different groups. Okay, so we've got a morning group that did all of their learning in the morning, came back in the evening, and came back the next day, right? And we have an evening group which did all of their learning in the evening, hopefully went home and slept, came back the next day, and then again 24 hours later. So we've got these 12-hour sort of epics in between testing. One thing we learned immediately about sleep was that college students don't sleep much. So there's a lot of variability in our sample too in terms of the sleep duration, which we can talk about if you like. And what do we find? Well, something rather interesting. So let's concentrate on this darker line here, the morning training group, which is also our top row. If you learned in the morning, you learned pretty well, you maintained it that day, and you came back the next day and you are practically no better than chance, right? The learning really tanked overnight. If you trained in the evening, you actually started out not being quite as good. The next day, you're a little bit better. And by the next evening, you are far outperforming the people who learned in the morning, okay? So this kind of pattern wasn't 100% anticipated. For one thing, we didn't really expect that they would end up in different places. The common finding from the sleep literature is that sleep sort of serves to restore things, whether you learn in the morning or the evening. But what we hypothesized as interesting about this kind of training is that if you are someone who's learning a non-native contrast and you're doing it in the morning, something happens to you throughout that day that could really mess up that learning. And that something is going about your day speaking English, right? You hear many, many examples of D sounds that don't match what you've learned. And we know from the memory literature that activation of really similar kinds of information over the day before consolidation can really mess with your consolidation of that information. And so we've suggested, and we have, some replication of this, that learning in the evening or an epoch close to sleep might actually help you lock in that information slightly better. To follow up, we also extended this to a population of interest that has actually been shown to have speech sound, or rather sleep disorders, and also really struggles with speech sounds, which is adults with developmental language disorder. So these are folks who are college students. Their language is good enough to be at UConn. They often find themselves in majors like physics and math, where they don't have to do a lot of reading and writing, because that's something that's really doesn't come easy to them often. Here, what we did is a very similar kind of study, but we only assessed them twice. And what we added was an electrophysiological measure where we really testing their sensitivity to this sound contrast difference, because we were really also a little bit worried that potentially what could happen is maybe biases in responding or attentiveness that could change over time. And we really wanted to make sure that this was instantiated in the neural response as well. The good news was, I'm actually not even showing you the neural data right here, but the good news was that people did improve overnight. Of interest, we found that there was a really good correlation between the number of minutes you spent in a phase of sleep called light sleep that we expect to be related to the stabilization of perceptual skill, and how much better you did overnight. So not only was sleep related or improvements related to sleep period, but the amount of time you spent in this particular phase of sleep seemed to affect your gains. Adults with developmental language disorder, unfortunately, did not show this pattern, right? So they did not show improvements related to sleep. And in fact, they struggled more with discriminating non-native contrasts in general. And so Sayako has really taken this into her own independent career, really asking this question of whether some of the language-related difficulties we see in kids with developmental language disorder might be somehow linked to issues with consolidating lots of kinds of information, but potentially speech sound information as related to sleep. Okay, so to wrap up the kind of non-native learning part, we also wanted to look for evidence of generalization, because we know that sleep seems to aid in generalization. This is a small scale study that really looked for generalization between 2 similar sounding talkers. Here I've put them as Mr. Burns and his assistant. But they weren't those people, obviously. They were just 2 similar sounding Hindi speakers. Here we looked for learning on one talker, and then how well that transferred to this new talker. And what I'm showing you here on the bottom plot is basically evidence of transfer to that new talker. Here, what we're seeing is that if you're in the morning group, you show no evidence of generalization on that same day, right? But overnight, you do show some evidence that you've learned a bit. It's not dramatic, but you've learned a bit. If you've learned in the evening, you actually also show a sleep-related benefit for generalization. Unfortunately, that seems to go away, and it's a little mysterious why that goes away. It may be related again to that kind of interference story that we told before. So much like in word learning and motor sequence learning, sleep seems to aid in non-native speech sound learning in terms of stabilization and in generalization. Okay. What about in native language perception? So this is also work by a former graduate student, Shin Xie, who was interested in American English listeners' ability to adapt the speech of accented speech, right? So again, similar problem. We have a complex space and we have to learn the boundary through that space. She decided to use a contrast between word final voicing of stops. So if you're not familiar with the acoustics of these stops, I'll give you a really quick tutorial. If we have a word like bud, what I do as an English speaker to distinguish that from a word like but is actually mostly in the vowel length, believe it or not, right? And so you can see that in the first orange block up here, the vowel length for bud is long and for but it's pretty short. And she sampled from a bunch of English speakers, and sure enough, that's the thing that distinguishes bud and but for English speakers. When we get to Mandarin speakers, however, many of them tend to use a very different cue. And my understanding is that Mandarin doesn't have word final alveolar stops. And so they've sort of invented a way of signaling this voicing contrast. So they do it consistently, but it's not the same cue that I might use. So you can maybe get a hint of it up here. Here's a Mandarin speaker's bud on the top and but on the bottom. The vowel length is exactly the same. But what's different here is primarily the length of the burst. So the duh has a very short burst and the ta has a very long burst. And I'm going to play for you two examples. The first one is bud, the second one is but, and I hope you'll hear the distinction, but initially they may sound like the same word. So let's give it a try.
But.
Okay, did you get it? So but versus but, right, with a longer burst at the end. So when English, native Iowan ears like mine are tasked with perceiving this distinction, what we need to do is learn to attune to this new difference between that final voicing length rather than the vowel duration. The data is a little bit difficult to display in a way that's digestible in this format, but essentially what Shin was able to show is that when we train on one Mandarin accented talker and then test on a new talker, you see much better evidence of generalization to that new talker on day 2. So after a period of sleep, I keep confusing those words. After a period of sleep, listeners seem far more willing to take what they learned about Mandarin talker number 1 and apply it to Mandarin talker number 2. So going from sort of the specific instances to the more general category. So that's sort of the analogy there, right, from our previous study. So taking scores so far, we've got some similar neural machinery that seems to be used, or at least similar recruitment of frontal areas for native and non-native perception. We have a similar role for sleep in stabilization and generalization of learned information, whether you're dealing with native language or non-native speech categories. So then the question we asked is, all right, do these things all go together, right? So we know that people are wildly different in their ability to learn non-native contrasts. So that's maybe something that you can observe in the sort of variety of accents you might hear among very proficient speakers who've been in the US for a long time. Some might have a very strong trace of their native language. Some might have very little trace of their native language. That's absolutely true in lab-based studies as well. So my former student, Chris Hefner, was funded by an NSF grant to go after this question, which is there some sort of shared substrate for adapting to native language speech and learning non-native speech? And we we called it phonetic plasticity, and you can decide that's whatever you think it is, but the notion is that both of these rely on this ability to sort through the complex acoustic signal, find a new boundary between it, and maintain it over time. So how did Chris go about this? Well, let me tell you, if you're doing individual differences work, I should say first, you need to do a lot of work to make sure that the measures that you take are themselves stable over time, right? Because it might be that we see variability because this person was hungry and this person was cold and this person was stoned, which unfortunately happens here. So we don't want to be measuring that kind of variability. We want to be measuring the kind of variability that's really characteristic of the individual and is going to show up day after day or on different materials. So Chris first did about a year's worth of work to sort through a whole bunch of measures of learning and adaptation to find those that we knew were going to be pretty consistent within the individual over time. Now let's put them all together and see if they go together. So I'll walk you through real quick what his measures were, just so you get a flavor for it. He chose 2 measures of non-native category learning and 2 measures of native language. We can call them adaptation. They're also just sort of dealing with difficult or unusual situations in native language speech perception. The non-native measure, the first one we did was what we called the incidental learning paradigm. It was gamified in a really fun way. So Chris had a bunch of sounds that were actually German fricatives, but he just had the sound itself excised, so it sounded kind of like a noise burst. You were told that you are in the middle of a zombie apocalypse and that your task is to slap zombies. Zombies are going to appear in one of these 3 windows, right? And so eventually you'll see a zombie and you'll be asked to click on the button that corresponds to that window as fast as possible, and a little broom appears and it slaps the zombie. Now, unbeknownst to the listener, the relationship between some sounds that appear just before the zombie appears and the window is totally predictable. Okay, so we've taken that continuum and divided it up into 3 chunks. And depending on that sound, you should be able to learn which window the zombie is going to appear in. So what we see is people get better and better at this game as they've may or may not know, but have implicitly learned the relationship. And then on about block 7, we scramble those cues. So it's no longer predictable anymore where the zombie occurs. And what we see is in people who've learned, they slow way down, right? So they no longer show an advantage for that getting to the zombie in the right amount of time. It's a really fun task. We also did something much more boring, which is basically the same task, only now it's just 3 boxes, right? So, hit the blue box, the yellow box, or the red box, and you get feedback about whether you got the right choice. Okay, so much more standard kind of training paradigm. The native language measures, again, like I said, they took a little bit of finessing to figure out good ones. We did one that was a rate adaptation test where we sped up speech and we looked at ability to identify keywords in the speech. I'll start you with the easy one, which for me is very hard. So you hear something like this.
The young pins are to get it in pipes with feet.
Okay, and then you get a few options on the screen about words that might have appeared there, and you can advance to the next level if you get them right. And if you get really good, you can do this.
A horse and a cruiser dangling apart.
And I can't tell you what's in that, but apparently some of our younger listeners can. They can adapt and reliably tell you what words appear in that kind of feta speech. And then we do it adaptively. So you kind of bounce up and down between these levels depending on your performance. We do something similar with accent perception and noise. So we have one at an easier noise level, sounds like this.
Nudge the dark time to try the wagon.
You might have heard the word wagon, perhaps.
He dents on his old boot into the tinsel and felt.
And if you learned something about that talker, you would have heard the word pencil, and you would have learned that he's an Italian talker and his vowel for pencil maybe is not quite what you would expect. Okay, so there's a lot of really rich data here, but what Chris and I were really concerned with is what kind of variant structure describes this data. Is it the case that people who are all good at one learning are different from the people who are good at adaptation, or is it really one kind of ability that underlies all of them? And without going into the details, the winning model ended up being one where all 4 of these tasks really loaded heavily on one factor that we're calling plasticity here. Now, just to make sure that it wasn't the case that good participants are good at everything, we had some other types of tasks that were completely unrelated to this. We had a speed task and a some other things, a working memory task that were just simply unrelated. So that's comforting to know that it isn't just subjects who are trying hard versus those that aren't. So it does seem to be the case that if you are someone who is good at adapting to native language speech, you tend to be better also at learning non-native speech. Okay, so I have exactly the right amount of time left. So I'm going to continue on to something that's a little bit newer that throws a little bit of a monkey wrench into this, because so far I've been building this argument that yes, these things are sort of different flavors of the same thing, right? That whether we're dealing with native language speech or non-native speech, similar machinery is involved in all cases. And this maybe goes back to maybe my very first interest in cognitive science, which was categorical perception. I'm sure most of you know what categorical perception is, but for those of you where this is new, it's this notion that in speech sounds, if we take tokens that are equally spaced across an acoustic continuum, that tends to be not how we perceive them. Instead, we perceive them as being much more starkly different from each other, and we have trouble distinguishing between items that fall into different categories. So here's just one example. These are old stimuli, but they do the trick. We're going to go from one category to another, and I promise they're equally spaced, but what you'll probably perceive as a real sharp boundary and then a change to a different sound.
Da, 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 da.
Okay, so I heard 2 da's and 3 ta's. You may have heard something similar. This is a really robust phenomenon. Well, this idea of categorical perception, or this idea that we have kind of collapsing around these category centers perceptually, has been connected to the non-native perception issue in the following way. Oh, wait, I was first going to explain that there's a lot of variation in this. Sorry, took me a little off track. So before we get there, it turns out that when we look at categorical tasks, not everybody is the same, right? So on balance, people tend to be very categorical, but if we ask people to rate tokens along a continuum, and here we're using sa and sha, but we've also done this with other types of speech sound contrasts. We ask them to rate things as, okay, is this token most like sign or most like shine? Some people, like the person on the left, actually will kind of track the incremental difference for each stimulus as you go up, and they show this very linear kind of behavior. Really looks like they are perceiving these acoustically, one sort of after the other. Other subjects will be very categorical, right? They say, nope, all of these tokens as I go across the continuum sound just like sign, and then I'm going to get to one, and then the rest of them sound just like shine. Okay, so the way these things connect up is in the following way, and it's really motivated by theories from a number of speech scientists, but I think Kathy Best may be best known for this idea of perceptual assimilation, right? Which is that we know that non-native categories that fall within the boundaries of a native language sound, like these Hindi, dental, and retroflex sounds, they are particularly squirrely to learn, right? And the idea is that, you know, because you have learned not to perceive differences among Ds as part of being categorically perceiving, these things must be even harder to crack apart because of that. So that's the PAM, the perceptual assimilation model. This is also PAM. This is my former student, Pam Furmeister, who by coincidence worked with this model a lot. We had a lot of fun with that. But she really was curious about this hypothesis and pushing it on it a little bit more. And she said, okay, well, the PAM, the perceptual assimilation model, seems to work across languages, right? Predicts which contrasts are going to be hard for a given language background, but does it work for the individual, right? And the notion here is, if you are a very categorical perceiver, shouldn't you also be someone who is really bad at learning non-native sound contrasts, right? Someone who really finds it even more difficult to tease apart that sound contrast. So this was Pam's dissertation. She's gone on to a postdoc in Germany, and she did a number of really beautiful studies, but I'll highlight a couple here. So here's one where she basically combined, old studies we had and put them together. She asked, all right, how categorically do you perceive? And she did 2 sound contrasts, a sign shine contrast and a ba da, just to kind of throw things around. And then did a non-native speech sound training, much as you've seen before. And the question is, does the one predict the other, right? Is it the case that more categorical people are the ones who struggle more with non-native sound learning? So here are the relationships between non-native learning and categoricity, as I call it. And essentially there are none, right? So we were unable to find any relationships between your behavior, your individual differences in native language, and these differences in non-native learning, okay? So at the individual level, this relationship is not detectable by us, at least yet. We thought maybe we should go about this a little bit more aggressively, because we kind of just threw in 2 different sound contrasts and try to see how things fell. And I think we had about 60 people in that study. So this is work that's under review right now. So this is brand new data. Here, Pam again assessed how categorically you perceive sign and shine and ba and da, but then tried to also match this up with your perception of 2 contrasts that are going to be a little more closely linked to each one. So she had a Polish fricative contrast, which sort of lives in that sign shine territory, and our Hindi stop contrast, which again are close to those da sounds. Again, those of you interested in online data collection, we did this on Prolific, which is a way of getting online data, and I can talk about that if you like. So far, after 250 people, still no relationship at the individual level. Okay, so I don't think we need to abandon the perceptual assimilation model at all. I think it's still very useful for predicting these cross-linguistic differences, but so far it's not panning out at the individual level for predicting why some people end up being great non-native learners and other people don't. So you might ask, well, does anything predict this? Do we have any clue at all why some people are good non-native learners? Pam Furmeister has also answered this question. We find that, interestingly enough, the ability to learn, but also just to perceive these contrasts, is among the many individual differences measures we've taken, best predicted by a measure called sound blending. Those of you who've done any kind of reading research will be familiar with this. It's a component of a lot of reading tests. It's the kind of thing where I ask you to say, okay, what's cat, but take off the k sound, right? And these items get more and more difficult. People who are good at that sort of more meta-phonetic, meta-phonological task are those who end up being better even before learning, but especially learning later on. Because this is a language and brain thing, I should also mention that there are brain structural differences that also seem to predict how well people learn. So this is a study that Pam Furmeister did, again, as part of her thesis, where she collected structural brain MRI data from a number of people and looked at a whole bunch of different kinds of measures. One that really had the most power in terms of predicting your sort of categoricity and also your non-native learning was the gyrification of the right and left temporal lobe. So this was, interestingly enough, a negative relationship. So you might think that gyrification refers to basically how kind of deep those folds get in your brain. You might expect more of that is better. That is in fact not what we found. And so we're still in the process of digging into these sort of cytoarchitectonic differences, these brain structure differences, to understand why it is that some brains might be sort of set up better to perceive native language sounds in this case, but also perceive non-native sounds. So much at work to be done there, and I hope maybe another 5 years to come back and give you a bit more conclusive answer on what kinds of differences in the brain, both structural and functional, are the best predictors of native and non-native adaptation. So returning to our question, right? So is native language speech sound perception like non-native speech sound perception? I would say on balance, the jury says yes, right? I think that brains and systems don't like to reinvent themselves, that we seem to be using very similar machinery for non-native speech perception as we do for native speech perception. That said, at the individual level, the connection between these skills is a little bit squirrely in the ways that I've already told you. So I think there's a lot more really interesting work to be done to try to understand what makes for the best conditions for non-native speech sound learning, what makes for excellent training kinds of paradigms for both native and non-native listeners. And those of you, again, who are involved in speech language hearing might resonate to that idea of what makes for a good training paradigm for a native listener if we're trying to improve comprehension. Okay, so with that said, I'd like to thank you for being so attentive and the many people who are involved in this work, some of whom are highlighted in recent pandemic era, unfortunately, lab photo on the left. And I'd be delighted to answer any questions you might have now. And feel free to chime in whenever you like. I know I threw a lot at you all at once.
I'll start then. So this was an excellent talk, Emily. I learned so much. Really nice, really clear. Thank you so much.
Thank you.
I have a question about the frontal areas of the brain being involved in the early stages of learning.
Yeah.
So to what extent does that relate that you involve more motor systems